Shapes are fairly easily dealt with. With the normal Mercator, scale expansion leads to shape distortion as the north-south distance from the equator increases. However, our cylinder is horizontal, not vertical. Therefore, on this projection, scale expansion leads to shape distortion as the east-west distance from the datum meridian increases. However, this is not usually a problem, as the chart is not normally used outside the 1% east-west scale expansion band. If we need to go further east or west, we use a chart with a different datum meridian. Chart convergence is complicated on this projection because it constantly changes. This is because meridians are mostly complex curves which constantly change direction. Near the pole, the parallels of latitude are not very elliptical. In fact, they are virtually circles. So as we have just said, the meridians will emerge radially from the pole in a very similar way to the polar stereographic. At the pole, therefore, the chart convergence factor is 1 because, just like the polar stereographic, there are 360 degrees of longitude represented by 360 degrees of angle on the chart. So the chart convergence is correct at the pole, which means that it is the same as the Earth convergence at the pole. Now consider the situation at the equator, which is depicted as two straight lines. As the meridians must cut these at right angles too, they are all parallel to each other at the equator. This means that the chart convergence is correct at the equator as well, because Earth meridians are also parallel to each other at the equator. So we can sum up chart convergence by saying that it is correct at the pole and the equator, but not elsewhere. How will rhumb lines appear on this chart? They follow the same pattern as meridians. The datum meridian is a straight line. The meridian perpendicular to it also appears as a straight line, and the equator appears as two straight lines. All other rhumb lines appear as complex curves. The depiction of great circles is fairly similar to rhumb lines. The datum meridian is a straight line. The meridian perpendicular to it is a straight line, and the equator appears as two straight lines. However, another family of great circles also form straight lines. Imagine the datum meridian like this. Now consider a great circle with its vertex on the datum meridian. In other words, crossing it at right angles. If we rotate the cylinder and Earth together so that we are looking at it end on, we see this. Now try to imagine what will happen when we shine the light at the centre. The projected shadow will appear as a straight line along the cylinder parallel to the projected equator. This is shown here on the projection. So, great circles are complex curves, except for the datum meridian, the meridian perpendicular to it, the equator, and great circles perpendicular to the datum meridian. This projection has three main uses, but one in particular should be remembered for examination questions. Its primary use is for large-scale mapping of long, thin countries with a large north-south extent and less east-west extent. The UK Ordnance Survey, for instance, uses a transverse Mercator projection, as can be seen from this note on the side of a 1 to 50,000 Land Ranger series. The CAA quarter-million topographical air charts of the United Kingdom series, which are widely used by helicopter and general aviation pilots, are also based on this projection. However, the transverse Mercator projection can also be used for flying routes with a large north-south extent and less east-west extent. And it is actually a better projection for polar flying than a polar stereographic chart, provided that the route is along or very close to the data meridian. The scale is completely correct all along the data meridian, and within 1% over a 1,000-mile wide strip. However, examiners are likely to concentrate on the first application, large-scale mapping of long thin countries with a large north-south extent and less east-west extent. So let's summarize these properties. We looked at scale. It's correct along the data meridian. Elsewhere, it expands as the secant of the Great Circle arc distance in the east-west direction. The chart is orthomorphic. It follows Mercator's rules for construction of the graticule. The graticule is complex. The data meridian, the meridian perpendicular to it, and the equator are straight lines. Other meridians are complex curves. Parallels of latitude are ellipses, except for the equator, which appears as two straight lines. Shapes follow the pattern of a direct Mercator, except that the distortion increases with the east-west distance from the data meridian. The chart convergence is also complex, but it is correct at the pole and the equator. Rhumb lines are generally complex curves, except for the data meridian, the meridian perpendicular to it, and the equator. Great circles are also complex curves, except for the data meridian, the meridian perpendicular to it, the equator, and great circles perpendicular to the data meridian.